Good morning, students. Today our topic is electric potential due to a point charge. Electric potential due to a point charge. To find the potential due to a point charge, let us assume a source charge is placed at point O, origin, and a test charge Q naught at point P. This is the point P, which is at a distance small r from the source charge plus Q. The distance of P from O is small r. Since Q naught is placed in the electric field of the charge plus Q, so it will experiences a force Q naught into E. Q naught into electric field. Now, to keep the charge Q naught at point P, an external force F is equals to minus Q naught E is applied. Let the charge Q naught travels an infinitesimally small displacement PQ is equals to dl, and so work done in traveling this displacement is given by dw is equals to f dot dl, and if we put the value of the force, then we get dw is equals to q naught e into dl. This is the small work done. Now, since dl is equals to minus dr, since distance small r decreases in the direction of dl, since distance small r decreases in the direction of dl in this diagram, the displacement dl is equals to pq, and its direction is from P to Q. Now, so in terms of the dr, we can write the work done dw is equals to minus q naught e into dr. On putting the value of dl is equals to minus dr, we get dw is equals to minus q naught e into dr. Now, electric field E is equals to kq upon small r square. If we put this value, then we get dw is equals to minus q naught kq divided by r square into dr. dw is equals to minus q naught into kq upon r square into dr. If w infinity to a work is done in moving a vanishingly small positive test charge q naught from infinity to a. Now, the infinitesimally small charge q naught is moving from infinity to a, point A. This is clear in the diagram. The positive test charge is moving from infinity to a point. Now, in this case, the total work done is equals to integral from infinity to a dw is equals to minus k q naught into integral from infinity to ra dr divided by r square. If we solve this equation on integration, we get total work done in moving the positive test charge from infinity to a is equals to k q naught divided by ra. Now, according to the definition of the potential, that potential at point A, which is equal to VA, is equals to work from infinity to A, W infinity to A divided by Q naught is equals to KQ upon RA. And in generally, if we remove the subscript A, then we get the formula for electric potential due to a point charge is given by V is equals to kq upon small r. If small r is the position vector of q and r dash of q naught, then in terms of the position vectors, the potential is given by V is equals to kq divided by modulus of r minus r dash. Now next topic is relation between electric field and electric potential, or we can say the field as the gradient of potential. Let us consider A and B are 2 points in an electric field. Both are separated by a very small distance. AB is equals to minus dr. Now both the points A and B are so close that electric field intensity between these two are equal to E. Both the points are so close that the electric field intensity between these 2 points are equal to E, and dV between any 2 points A and B is given by work done in moving a unit positive test charge from A to B. This is the potential difference, and dV is equals to q naught E into dr, q naught E dot dr. dV is equals to q naught E dot dr, and dV is equals to, we know that the angle between the E and dr is 180, so we get dV is equals to E dr cos 180. On putting q naught is equal to plus 1, we get dV is equals to minus EdR, and finally we get E is equals to minus dV by dr. And in generally we can write it as E is equals to minus grade V. E is equals to minus grade V. And this is the relation between the electric field and potential. So the electric field is equal to the negative of the potential gradient. Negative sign indicates that the direction of E is always on the direction of decrease of the direction of decrease of V. Negative sign indicates that the direction of E is always on the direction of decrease of V.